All right. So we are in the middle of chapter 4. We might finish chapter 4 today. We might. By the way, we are about 1/3 of the way through the semester in terms of like number of classes that have gone by. So it might feel like we kind of just started, but we're doing pretty good. We've got, as I said, 1/3 of the way through. We're already about done chapter 4, and we're not going to be doing 12 chapters. But we had a couple quick chapters in there. So the ones that are coming up, some of them are a little bit longer and definitely a little more involved. So I'm kind of right where I think we should be right now. And in terms of even pace of the course, I'm trying to pace it appropriately. If you think I'm going fast through certain parts, I mean, I guess that's an inevitable way to feel in any course, but what I'm trying to do is apportion the time so that we have enough time to deal with the sort of more complex things when we get there. And I guess I'm wasting time right now telling you this, but that's okay. I'm the one in charge, so I can waste as much time as I like. Okay, so what we're going to do today, what we did last time is we looked at cyclohexane chairs that had 1, 4, like 2 substituents on there. And we looked at, there was the cis version and the trans version, and we did ring flips back and forth. And then we were able to determine which ring flipped form was more stable, and therefore whether cis or trans was more stable. And I think the conclusion that we came to was that trans 1,4-dimethyl cyclohexane was more stable than cis. So what I want to do is repeat that exercise, partly for practice, but partly not the exact same one, but we're going to look at the 1,3 and the 1,2. We've already done the 1,4 last class. And it's the same steps, it's the same procedure. And I think rather than go through the slides here, I'd be happier just to do it out on the board, on paper, as it were. So what I'm going to start with, let's do 1,2. So here's cyclohexane, where both of the methyl groups are coming towards us, or we can have a cyclohexane where one is towards us and one's away from us. So which one of these is cis, A or B? A or B? A is cis, that's good. Because both methyls are pointing the same way. They're both together, they're both up, I guess, as it was. Up, up. And this one, therefore, is going to be trans, and we call this one up and this one down. And if that's down, there's a hydrogen here that's up. And where the methyl is up, there's a hydrogen that's down. Okay. Same thing on the other one. We have a hydrogen that's back, a hydrogen that's back. If it's going backwards, we say it's down. If it's coming forwards, if it's a wedged bond, we say it's up. So what we would like to do is draw both chairs for each of these to give a total of 4 structures. And by the way, A and B are isomers of each other. What kind of isomers are they? They're not constitutional isomers. Stereoisomers is the name. Stereoisomers. So let's go ahead. Let's start with A. We're going to draw cyclohexane, and it's going to have a ring flip form. So we can draw both if we want to begin with. There's my rough drawing of my 2 cyclohexane rings. For some reason, I can draw the left side one like faster and easier than I can draw the right side one. But anyway, there it is. And we need to pick 2 carbons to be carbons 1 and 2. So in our ring, if we look at 1 and 2, why don't we go with 1 and 2? So carbon 1 will have a group that's up and a group that's equatorial, axial and equatorial. Carbon 2 will have an axial and an equatorial as well. Remember that the equatorial bonds should be roughly parallel to a bond 2 carbons away. So that this bond here should be roughly parallel to that one. And this one should be roughly parallel to that one. Now we got to just populate these positions that we just drew in with what we see in the structure. So on carbon 1, we would say the axial one that's pointing straight up is up, and the equatorial one is below it, so it's down. So on carbon 1 for A, cis, the up group is the CH3, and the down group is the hydrogen. If we continue around the ring and we go to carbon 2, the equatorial group on this one is up. And the axial one is down. It's pointing straight down. So the up or down, that's a relative term. We would say that the equatorial bond on carbon 2 is higher up, pointing more up, than the axial, which is pointing straight down. So the up one on carbon 2 is the CH3, and the down one is the hydrogen. So this is one chair flipped form. If we were then to do a ring flip, this is an equilibrium, what we would do is take 1 and we pull it down, so this becomes carbon 1 right here, and carbon 2 will be right there. Carbon 2 has an axial and an equatorial. Carbon 1 has an axial and an equatorial, like that. And then we just put the same groups back on. On carbon 1 now, the up group is equatorial, that's the CH3. And the hydrogen is the down group, it goes down. On carbon 2, the up group is the CH3. And the hydrogen is the down group, which is equatorial. So we have these two forms for cis. Both of these are cis. Two ring flip forms, and remember these can flip back and forth, thousands of times a second at room temp, and you're going to have both of these present at any point if you have a sample of this material. Now looking at these two structures, does one look more stable to you than the other? How do you determine stability when you're comparing these things? You look for how many groups there are in axial versus equatorial positions. Big groups prefer to be equatorial because it reduces van der Waals strain. So the left-hand structure has two groups, both methyls. One is axial and one is equatorial. What about the second structure? Again, one is axial, one is equatorial. There's not a clear winner here, is there? These are basically equivalent in energy. They're the same structure, so I would say, at room temp, you're going to have 50% this one, 50% that one. In fact, I don't think you could distinguish these two from each other. Okay, so neither of them is super happy because neither of them has both groups equatorial, but also you don't have the worst case scenario where both are axial. So both are sort of intermediate, I would say, in energy. So let's do the trans. Remember the trans has methyl up and a methyl down. So we're going to redraw our cyclohexane chairs like that. And carbon 1, carbon 2, carbon 1, carbon 2. By the way, it's arbitrary which ones you pick as carbon 1s and carbon 2 around here. Doesn't matter. So the CH3 is up and the hydrogen is down in the structure. It's going backwards. On carbon 2, we have two positions. The CH3 is the one that's going down. So right away, looking at that structure, what do you think? What's your initial thoughts on that one? Not good, eh? Why? Both axial, right? It's probably going to be the loser structure right there. 1, 2. 2 has 2 positions like that. And on carbon 1, the up is the CH3. The hydrogen is down. On carbon 2, the hydrogen is up and the CH3 is down. Notice here how that axial bond on carbon 2, the hydrogen, it's short enough that you can put the hydrogen inside the ring the way I did there. Where above, I think I made it long and extended out above. I don't care which one of those two you do. Just do one of them. Don't do something in between where you have like, just avoid that one. Just make it clean and visible. I don't really care which way you go. The second structure, how do you think that is in terms of stability? Yeah, it's the best one of them all. And why is that? Yeah, 2 equatorial groups. So this is most stable. This is least. And the 2 above are intermediate. So this compound here, probably if you made this molecule and put it in solution and let it flip back and forth, I don't know, this is total guess, but probably 98% would be in this form and 2% in this form if you froze it and counted how many were in either form. But it can still flip back and forth. It just spends less time in the diaxial position, right? So it's not very often you would find a molecule in the diaxial, but it can still happen. It can still form. It can still exist. Cool. So we would say the more stable isomer is going to be trans because it has a conformation that puts both groups axial. Sorry, both groups equatorial. And that's what makes this one more stable. Cis is always going to play second fiddle because cis always has at least one group that's going to be axial all the time. All right, let's do one more. Let's do 1, 3. By the way, for 1, 2 and 1, 4, the ones we finished already, in both cases, the most stable conformation was trans, or the more stable conformation, proper grammar here, proper English. Let's check out what the story is for 1, 3. 1, 2, 3, 4, 5, 6. This is again 1, 3. This one's cis. This one's trans. And let's go ahead. My fingers stopped working. Okay, my fingers work. My screen stopped responding to my fingers is what I mean. There's that. There's that. Carbon 1, I guess we could pick the same carbon if we want. Carbon 3 is down here. Carbon 1 has groups here and here. Carbon 3 has groups here and here. Carbon 1, we would say the CH3 is up and the hydrogen is down. Up, just why is it up? It's got a wedged bond, so it's up. On carbon 3, the CH3 is up and the hydrogen is down. Okay. Up or down, remember, on the cyclohexane ring does not mean axial or equatorial. Sometimes the axial is up, sometimes the axial is down. Do a ring flip. Carbon 1 is here, carbon 3 is here. Carbon 1 has the CH3 up, hydrogen down, CH3 up, hydrogen down. Which of these two forms is more stable? Left or right? Yeah, right. It's got 2 methyl groups, both in equatorial positions. This is the clear winner, this guy right here. Most stable, more stable conformation. Let's do the trans. Notice how we're getting faster at this. By we, I mean me. If anyone got the chairs game, did anyone get that? One person? Did you play? Are you good at it yet? Yeah. What's your best score so far? Okay, you're already ahead of me, so that's good. This will be a piece of cake for you when you get to doing this on tests and stuff like that. Okay. Now we have this one, which is the 1,3 trans. So again, we can pick 1,3. We can pick different carbons if you want. Do you want me to pick different carbons this time? I always pick the right-hand one as 1 for some reason, but here, I'm going to pick a different one just to show you I can. I'm going to go this way. Go on the top ones. Carbon 1, looks like that. Carbon 1 has the CH3 up, hydrogen down. Carbon 3 has the hydrogen up and the CH3 down. It's in equilibrium with this. So carbon 1 is here. Carbon 3 has bonds here and here. Carbon 1 has bonds there and there. Carbon 1, still CH3 is up, hydrogen down. Carbon 3, hydrogen is up, CH3 is down. Which of these is more stable, left or right? Both the same. Good. These are both the same. Both have one axial. Both have one equatorial. Looking at the whole thing, which do you think is the more stable conformation, cis or trans? Cis, right. Cis is more stable because it has the conformation here where both groups are equatorial. And again, this is probably 98%, 2% kind of situation. And so whichever conformation, whichever isomer can give you both groups equatorial, that's going to be the one that's more stable. Great. I'm going to show you one. This is going to be an exception. People love exceptions, don't they? How about this compound? This one, if you were to draw you can have this one, or when you ring flip it, you can draw this the same way as you drew anything else. It turns out in this example, this one is more stable. Diaxial is better in this case. Kind of weird, isn't it? Any guesses why that might be? Well, I'll take away your suspense. Draw EOH. Lone pair. What's that interaction called? Hydrogen bonding, yeah. This molecule actually prefers the conformation where they're both axial because it allows these two groups to hydrogen bond with each other. So hydrogen bonding is an attractive interaction. The methyls, if it's just methyls, they don't interact with each other at all, except negatively. They have van der Waals strain, and that's about it. But these positively interact, these two particular ones, the OH and the NH2. So almost everything I teach you in this course has exceptions. And I feel like researchers love taking rules and finding exceptions to them. Because then, well, it helps them build bigger rules and so on. In fact, most of the rules we teach, eventually we show you cases where they fail. And I mean, that's life, I guess. But even like one of the bedrocks of chemistry is John Dalton's atomic theory. And John Dalton's atomic theory has 5 elements to it. One is that all atoms of a given element are identical to each other. And that's not true. We know that there's isotopes, that different elements come in different, subtypes, I guess you could say. Another one is that compounds are made from fixed whole number ratios of elements. And we know that's not true either. We know of other substances that it's not a fixed ratio. You can have variable ratios. Another is that atoms can't be created or destroyed. And we know you can do that too in a nuclear reaction. And so it's one of these rules that, like, yeah, okay, we have this rule, and everything we're studying in this course is based on the assumptions of those rules. But yeah, there's a few exceptions. And so the general rule is that things are more stable when they're in axial positions. Axial conformations, cyclohexane conformations are more stable when the groups are able to go equatorial. But there are cases that that's not true as well. So I'm not trying to suggest that everything we teach you is a lie, but none of it either is 100% truth.
So then in a midterm, can you like put an exception to the rule, and then maybe we think of the rule and get it wrong?
I heard something there, but it's not coming up very loud. Can you type it?
Can you hear me now?
Here's another example. This is glucose. So glucose is sugar, right? It's a sugar that all of us need. It's, I think, the main sugar that is used in our metabolism, and more complex sugars that we eat get converted into glucose. Glucose has a 6-atom ring in it, right? 1 oxygen, but otherwise it looks a lot like cyclohexane with different groups on the side. And if you look at glucose, it has 2 possible structures. It has the structure on the left. The ring does adopt a cyclohexane-like ring, or the structure on the right. And in this example, on the left-hand side, you can put every substituent into an equatorial position, or you can put every substituent into an axial position. And it's true that these are mostly OHs and that there can be some hydrogen bonding going on here, but the more stable conformation is this one, and that's the one that exists in our body, in plants, and so on. It's one that's important. By the way, there's another, when you get into biochem, there's another method of depicting 3-dimensional structures called a Haworth, Haworth. Haworth projection. That's not the actual structure. It doesn't look flat like that. It's actually, it forms a chair like cyclohexane does. And these are just some other simple sugars: glucose, galactose, mannose. The variation between the different simple sugars, several of them, they all have the same basic structure, just whether these groups are axial or equatorial in the chair structure is what differentiates the different simple sugars from each other. Great. We're done with cyclohexane conformations, but we're not done with them. We're going to come back to the cyclohexane conformations when we hit chapter, I want to say 7. So don't forget them. They're good. We're going to talk about another type of spectroscopy, and this is called carbon-13 NMR spectroscopy. This is a little more, it's a more involved technique. It requires a much more involved piece of equipment. An IR spectrometer. Remember we did IR back in chapter 2 for functional groups, or 3, whatever chapter it was. Those spectrometers are pretty cheap. You can get one for like $40,000. And so we have a couple of those in the department. NMR spectrometers are much more expensive. So we have one. It's in the basement of ACMA. And a new one today is probably starting at about $500,000. And it looks like this. You can see the size of it based on the stairs to climb up to get to the top, and there's a dude sitting up at the top there. The one we have isn't quite that big, but the main part of the spectrometer is this big tank here. And the tank is largely to hold cryogens because it contains an outer wall that's filled with liquid nitrogen and an inner wall that's filled with liquid helium. And liquid helium is pretty expensive. It has a boiling point of 4 degrees Kelvin, extremely cold, much colder than liquid nitrogen. And the purpose of that is to keep a superconducting coil at a low enough temperature that it remains a superconductor. So a superconductor is a substance or a material that you can put charge through and there's no resistance. So there's a coil where it's charged up with a whole bunch of charge that spins around this coil, and it spins forever. As long as you keep it cold, you never lose any electricity. You never lose any charge. And because you have a spinning charge or a rotating charge, that creates a very strong magnetic field. So nuclear magnetic resonance spectroscopy is what NMR stands for. And so what it does is it splits different energy levels of nuclei, and it allows you to do transitions between them, and you can make measurements on the nuclei of atoms that you put inside. The very same technology is used in an MRI scanner. The MRI is called magnetic resonance imaging. It's basically the exact same thing, except it's a spectrometer that you can go inside of. You can go inside that very strong magnetic field yourself, and it can make measurements on your body. The magnet strength in the MRI scanners you see in hospitals are much weaker than the ones that we use in chemistry labs. So we have much more powerful ones for what we do. By the way, when MRI scans first came out, they used to be called NMRIs, nuclear magnetic resonance imaging, just like we use NMR here. But public were scared of going inside them because they heard the term nuclear. And when they heard of nuclear, people immediately associated that with like nuclear explosions or nuclear power plants, nuclear waste. Every time they've ever heard the word nuclear before, it was a negative. And so they dropped that off the name, because the nuclear has nothing to do with radioactivity or anything like that. Nuclear just means it's looking at nuclei of atoms. Just like infrared is looking at bonds, looking at vibrations, which allows you to identify functional groups, carbon-13 is looking at the nuclei of the atoms that are present. So carbon-13, as the name implies, is looking at the nuclei of carbon-13 atoms that could be in your structure. Now, this is great for organic chemistry because organic chemistry, most compounds are loaded with carbons, and this is allowing us to take a look at those carbons and get information about the structure of the molecule. Carbon-13 is not very abundant, though. Carbon-13 is only about 1.1% abundant, the other 98.9% being carbon-12. Carbon-14 is basically insignificant. It's enough to do carbon-14 dating, but crazy small amounts of carbon-14. Carbon-12 is the big show in town. Almost all the carbons are carbon-12, only about 1% carbon-13, but those are the ones we're looking for. So immediately, when you put a sample into an NMR spectrometer, you're looking for carbon-13s, already 99% of your sample is undetectable. That 1.1% is what we're going to zero in on. By the way, that 13, that's the number of protons plus the number of neutrons in the isotope. So carbon-13, we know all carbons have 6 protons. So that means it also has 7 neutrons. Carbon-12 has 6 and 6. Carbon-14, 6 and 8. Yes? Why carbon-13? Yeah, why aren't we looking at carbon-12, which is much more abundant? This gets into physics, but what happens is that only certain nuclei are what we call magnetically active, and carbon-12 is not. So it would be great if you could see carbon-12. It's just, for physics reasons that are beyond my understanding, it's not magnetically active. Carbon-13 is, though. Hydrogen is as well. protons. So there's another kind of spectroscopy that you might learn if you do organic 2 called proton NMR spectroscopy, which looks at protons. And since they're all over the place in organic compounds too, then you see them as well. Okay, carbon-13 NMR spectrum basically gives you, I'm going to draw it here, it gives you a spectrum which looks like this. The scale on the bottom is something called ppm, which starts for parts per million. And on the left side of the spectrum, it goes to about 0. This has an inverted scale too, just like infrared. And it increases in number going to the left. And for organic chemistry, we typically go to about 220 ppm. And then what you see are peaks, like that. And what you see is one peak for each distinct type of carbon that you would find in a molecule. So if you have a molecule like methanol, it only has one carbon. I don't want to put that there. I'm going to delete all those lines. Yeah, if you have something like CH3OH, you'll see one peak somewhere like that. Because there's one carbon, one peak. It's very narrow, nice and tall. And that would tell you, if you ran a spectrum of that compound, it would say there's one unique kind of carbon in this molecule. Okay. Let's say instead we have a molecule like CH3CH2OH, which is ethanol. There you'll see two peaks because there's two carbons. And they come in different places because they have different environments. The carbon on the left up here is bonded to another carbon. The carbon here is bonded to a carbon and an oxygen. So it would come in a different place than the carbon on the left. Now, here's a skill testing question for you. Let's take cyclohexane. How many peaks do you think you'll see for cyclohexane? One. You know why? They're all the same. There's nothing to distinguish any one of those carbons. So maybe, I guess you can think of it like there's 6 peaks, but they all come in the exact same place. So they're like they all stack on top of each other. But the result is you only see a single peak here. You only get one peak. Okay. If you had something like methyl cyclohexane, this is a really skill testing question. How many peaks would you see for this? This one you see 5. And that's because there's this type, there's this type, and that's the same as this one. There's C, which is this type. There's D, and there's E. So you see 5 peaks. And you're like, okay, why is there 5 peaks for this one? Well, let's go back. I don't want to get too far ahead of myself here. So there's 2 pieces of information you get from the spectrum. One is the number of peaks, is the number of types of carbon in the molecule. Number 2 is where it comes in the spectrum. Chemical shift, just like infrared, where it came in the spectrum told you what kind of bond it was, whether it was a single bond, a double bond, a triple bond, bond to hydrogen, etc. Where it comes tells you about the environment, and it tells you about the hybridization as well. So let's look first. We said about 0 to 220 was the scale that we're looking at, and 0 is defined as where you see a carbon in this molecule, which is called tetramethylsilane. This is a cheap liquid you can buy. You can add it to your sample. That's going to come up and give you a peak at 0. If you have just a regular sp3 carbon, you know, like an alkane, then it's somewhere typically 0 to 30, 0 to 40. It's on the far right side of the spectrum. That can be stretched out to about 70 if you have an sp3 carbon with an electron withdrawing group attached. So if you have something like F, where fluorine is a strong electron withdrawing group, it's electronegative. We saw these before, I think, in the acid-base chapter. That can pull a peak to the left. We say it shifts it downfield, shifts it to the left. More electronegative atoms, get two fluorines, would shift it more to the left. SPs sort of come in this range here, 60 to 100-ish, and everything's ish, right? That's because there's lots of variation depending on the structure that you're looking at. Alkene sp2 somewhere between about 100 and 130. Aromatics, which are also sp2, covers much of the same range but can go out a little bit further. I'd say it's pretty rare for an aromatic carbon to go past 140, 150. Can happen. And then carbonyl carbons, which are also sp2 hybridized, are somewhere from 160 up to about 220. So these are all types that we've seen before, right? These are carbonyl, these are, and then we have over here alkanes. Electron withdrawing groups, electronegative atoms to the left of that range, without those to the right of that range. This table here appears on that data sheet that you guys were allowed to use for the oral test, and you can use it for future tests and exams. So the exact cutoff points of each of these ranges is shady, it's it blends from one to the next. So you have to think about what's reasonable given the molecule that you have. All right, cyclohexane we already looked at. Cyclohexane, we said we have a single peak. And how can you look at that and know that all these are the same? Well, two carbons will be the same as each other if you can do a plane of symmetry that reflects one to the other. So what that means is look at this molecule here. I'm going to draw a dotted line through here, and imagine that dotted line is a mirror. If anything on the left is the mirror image of what you see on the right, those two that are mirror images of each other will be indistinguishable from each other in carbon-13. We say they're related by symmetry. So that means that this one and this one are the same, and this one and this one are going to be the same too. Are there any other lines of symmetry in this molecule? Yeah, there's a bunch. You could also draw a plane of symmetry down that way, which means that this and this, these two atoms are mirror images, so that's A and A. Also, this one and this one are mirror images. So we know that A equals B. So if that's the case, let's call this A and call this A. And we know that this atom and this atom are mirror images through that line. So everything's A. We're all A's, right? So if you can do planes of symmetry that make any two atoms map on to each other, those will be equivalent and you won't be able to tell them apart. And they'll give you a single peak in carbon-13. That's a good thing too, is you can take a molecule, you can put it on paper, you can draw all these lines and think you got them all or whatever, but the spectrometer doesn't lie. It knows what the geometry of this compound is, knows how many peaks to show you, and sometimes you don't understand it right away and you scratch your head, but you have to come around. You have to believe what the instrument tells you. Cyclohexene. It's got 3 peaks. Now, cyclohexene doesn't have near as much symmetry, as many planes of symmetry as cyclohexane. All it really has is this dotted line here, which is a mirror plane. Right? You can't really draw any other, well, you can't. There's no other mirror planes that you can draw in this molecule. Nevertheless, you have A and A, you have B and B, you have C and C. Those are mirror planes. Those are equivalent to each other based on that mirror plane that we drew. And we see 3 peaks, A, B, C. So how do I know that one's A and one of those other two down on the right aren't A? Well, that's got to be A because of where it's coming. You know, I don't know what the number is, maybe like 128 ppm. Go back a few slides. 128 kind of puts you in the alkene region, right? Somewhere up there. So that's an sp2 carbon. And that's the only sp2 carbon in the structure. The other two, which are B and C, are these two. Which is which, I don't really know. In fact, you know, they're so close together that you could guess and be wrong. So it doesn't really matter to assign every one of them exactly, but we know one of them is B and one of them is going to be C as well. 1,3 cyclohexadiene. This is another ring and it's got two. Think about this molecule for a second and think about planes of symmetry. How many planes of symmetry can you find in this molecule? Or can you find any? Yeah, there's one. And that plane of symmetry goes down that way. So the left-hand side and the right-hand side are mirror images of each other. You have A and A, B and B, C and C. A and B are both sp2. And so you see those two up there. C is sp3. It's down there around 20 ppm. Good so far? Easy peasy? Great. 1,4 cyclohexadiene. Look at this one. What do you see for mirror planes for this? There's two. There's the vertical one. There's also a horizontal one that goes that way. So that means if you look at this atom A, its mirror image on the right is also A. And if you look at the other horizontal mirror plane, that's A and that's A. You see why that's the case? We have the other type, which is B, and it has a mirror plane, which puts this as B as well. Maps those onto each other. So for this, we only see two peaks. We see A and we see B. I notice A is a little taller than B. Don't read too much at this point into the height of the peaks, because there's lots of factors that go into the height that we're not going to get into. There's something called the nuclear Overhauser effect that causes carbons with hydrogens to be taller than carbons that don't have hydrogens. We're going to ignore that. Don't even think about the heights, because it can lead you to some incorrect conclusions for sure. Benzene. Benzene, we just get one. Why do we just get one for benzene? Yeah, it's got a huge amount of symmetry. They're all the same. You know, that makes that an A. In here, which makes this and this also A. And you have a plane here that makes this and this A, and then therefore that A as well. So yeah, whole bunch of symmetry here, one peak. So the more symmetrical the compound, the simpler the spectrum becomes in terms of number of peaks. Heptane. 7 carbons, right? C7H16. How many peaks do you see, first of all? 4. Do you see any symmetry in the molecule? Yeah? Plane of symmetry right there, where you get A, B, B, C, C, D, D. And then so you see A, B, C, D. I don't know which is which. Doesn't matter. They're all in the same region. They're all sp3. There's nothing really in this molecule that would make me strongly feel one was one versus the other. It's possible to have peaks that overlap, that show up in the same place, But that's usually not much of a problem because the peaks are so narrow, it's very unlikely they're going to have the exact same number. But it does happen sometimes. The fancier the instrument you buy, the less likely it is because you can get bigger and bigger magnets that make the lines narrower and narrower. The one we have is a 300 megahertz, which is decent but not great. I think the biggest one in the world is around 1,000 megahertz, and the biggest one in kilowatt has 900. So it's like 2 floors. So it would start on this floor and go upstairs, and you have to go upstairs to put the sample in and then come back down. We have no need for that. But people put big molecules in those, like proteins, and you can do carbon-13 spectra on a protein and you get thousands of peaks because there's so many different carbons in a protein, but they're able to make sense of that and make use of that information. Octane. Octane has 4 peaks as well. Do you see any symmetry in octane? No. But it has symmetry, but not the way I drew it. Okay, so look, think of it this way. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to do a rotation around the carbon-4, carbon-5 bond. And I'm going to redraw octane to look like this. 6, 7, 8, 3, 2, 1. I'm going to draw a different conformation. It's got a mirror plane now. We have A, B, B, C, C, D, D, 4 peaks, 4 peaks. So that probably makes you feel uncomfortable. I gave you a structure and you're like, I can't find any mirror planes in the way you drew it. And the instrument knew, right? The instrument knew there should be 4 peaks here. They're equivalent. And when you think about it, this is a new element of difficulty. If you can draw a conformation which has mirror planes and makes them all equal, then they are equal and they'll appear as one thing in the NMR. Remember, these molecules are spinning around very, very rapidly, and the NMR is actually a slow measurement. So basically it takes like a second for it to make a measurement on a molecule, which is a long time, because in that second it can go through every possible conformation 100 times. And so what it really sees is the average structure. So I mean, maybe another way to remember it is if you have an alkyl chain, doesn't matter how long it is, you can just start counting from the ends. The ends will always be the same if it's just a straight chain. And count inwards. C, B, C, D, D, E, E. This would have 5. Two-methylhexane. This one's a little more complicated, isn't it? This one doesn't have any symmetry, really. Okay, there's 2 peaks that can come together. So this one, starting at this end, there's A, B, C, D, E, F, F. Those 2 methyls are the same because you could draw a conformation How many do I got here? 1, 2, 3, 4, 5. 1, 2, 3, 4. So if you draw it like this, so you're looking at it down and the zigzag is going up and down away from you, this has a mirror plane which makes those 2 equivalent to each other. So this looks complicated now because now it's like, okay, I got to think about the molecule. I also got to think about any possible conformation that I could possibly conceivably draw that makes these equivalent to each other. The reality is that you don't have to do this every time. There's like some simple rules that if you follow, you'll get it right. So for example, if you have 2 methyls on the end of a chain, like this, they'll always be equivalent. In fact, if you have a T-butyl group, they'll always all be equivalent too. Okay. Don't worry, we'll see some more examples. Let's look at this one. This is symmetrical. It may not look it, right? But what we have is we have A, and the other side of the molecule is the same. In fact, there's other symmetry rotations besides reflections that you can do. If you put a point in the middle and rotated the molecule around 180 degrees, that and that would map onto the two structures we already drew. So we have A, we have B, and we have C. And we see the same thing here, A, B, C, in this compound as well. Carbon-13 is fun. How about this one? Take a look at this structure for a second and just think about it. We see two peaks. Why do we see two peaks? And what carbons belong together? And what carbons are different? So all these outer ones are the same, which gives you probably the tall peak. And then we have B and B here. So this is a little bit mind-bending, but once you kind of get the hang of how this works, it becomes quite straightforward. You know, this one, Adamantane. That's a real molecule, by the way. I think it inspired the writers of X-Men, the movies, because adamantium is what's in, what's his name? Wolverine, yeah. His skeleton, or his, whatever they add to his skeleton. Anyway, it's maybe this compound, who knows? Except they say it's magnetic metal in the shell, because Magneto can control his body. My wife, by the way, was in X-Men X2. Well, she wasn't like in the movie, but she was in the DVD special features. They shot the movie in Victoria when we lived there, and she went to watch the filming. And some of the actors came down, like Hugh Jackman and Patrick Stewart, and they came down to the people there and were signing autographs. So she got an autograph, and it's like a bunch of like kids and then her. Anyway, it's kind of funny. Hope she's not watching the YouTube stream here. This compound, by the way, has two kinds of carbon. It's got the ones that are CH2s, and then it's got the ones that are CHs. Lots of symmetry in this one too. Typically, the ones we give you will be less complex than adamantane. All right, it's past time. It's 9:24 now, so I'm going to stop talking. And we're pretty well done. How many more? Yeah, there's a couple more I got to do. So I got to clean up the rest of Chapter 4 when we have class on Friday. And goodbye, everyone.